So in this mini lecture, we're going to look at what a sequence is. So a sequence is a list of numbers that are generated by some mathematical rule, and it's typically expressed in terms of n. So it's just a list or a collection that we have, a collection of some numbers that's created by some defining rule. So we can write it as a list, or we can put it in braces within that type of notation using the variable n. So let's say we wanted to find the sequence of odd numbers or sequence of odd integers. We could do this and it'll be generated by 2n minus 1, right? So let's see how the sequence develops as you plug in integer values for n beginning with 1. So if we start with 1, 2 times 1 minus 1, okay, and then we'll do 2 times 2 minus 1, and then 2 times 3 minus 1, 2 times 4 minus 1, right? So what do we get here? We'll get 1, 3, 5, 7, right, and so on as we continue that sequence. So just by looking at it on your own, you see how it generated the odd integers, right? We just said 2 times anything must always result in an even number. And then if you subtract 1 from an even number, then it'll result in an odd number. So you might have been faced with similar problems like this in previous math courses. So the hardest part or the trickiest part might have been trying to figure out that defining rule, that mathematical rule that creates your sequence. So now we go into sequence convergence. So your main point or your main goal when dealing with sequences is going to be to figure out whether or not they converge. So if a sequence is convergent, then the terms in it will approach but really never reach some limiting real number value. So I'm saying some limiting value because you're going to use a limit at infinity to figure out whether or not a sequence converges or not. So mathematically, we say that a sequence, we'll say the sequence A sub n, a sequence converges if the limit of A sub n as n approaches infinity, if this exists, then we say that the sequence converges. So you're looking to see how your sequence responds or acts as the n value gets very, 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 very large, which means you're looking at the behavior of the sequence way down its list of numbers. So if we hop into this example, is the sequence 0 over 1, 1/4, 2/9, 3/16, 4/25, and so on, convergent or divergent? Okay, so let's hop right into this. So first, you're going to need to come up with that general mathematical rule to show this sequence or to define this sequence. So the first term, n equals 1, is 0 over 1, right? That first term, n equals 1, is 0 over 1. The second term, n equals 2, is 1/4, right? Just from looking back up at it. So if you look at it, the numerator is 1 less than n, and the denominator for each term is n squared, right? Let's write that down. So the numerator is 1 less than n, and the denominator for each term is n squared, if you take a look at it. So the same pattern holds true for all the other terms. So it looks to me that the sequence is n minus 1 over n squared. All right, so now we have to see if this converges. So to see if it converges, then what we're going to do is take the limit as n approaches infinity of n minus 1 over n squared. So now you just have to think back to your Calc 1 days. Say, okay, let's remember how to do these limits at infinity. So we can either use L'Hopital's rule, or we could compare degrees of the numerator and denominator, right? And either way, what do you get? You get a limit of 0. You get a limit of 0. So since the limit exists, right, the sequence does not increase without bound. The limit exists. It does not the sequence does not increase without bound. Then the sequence converges. Okay, so now our next question is, what is a series? What is a series? Well, a mathematical series is really similar to a sequence, but instead of just listing the numbers in sequence, you actually add them together. So instead of listing the numbers in sequence, we add them together for a series. And then a series, they're also a little pickier about whether you start, about where you start and end at. So series, they are based on sums, while sequences are not. So let's take a look at the simple series where we have summation as n goes from 0 to 4 of n squared plus 3. Right, so they have the sigma notation in the front, right? And then it goes from 0 to 4. So we start by plugging in the bottom bound of 0 in for n, and then plug in consecutive integers until you reach the top bound, which is the 4, which that'll be your last term. So remember, it's a series, so you have to add all the results together. So here we're going to get 0, we're starting at 0, 0 squared plus 3. And we add that to 1 squared plus 3. Add that to 2 squared plus 3. 3 squared plus 3. And then add that to 4 squared plus 3. Right, what do we get? Looks like 0 squared plus 3 looks to be 3. 1 squared plus 3 is 4. 2 squared plus 3 is 7. And then plus 12 plus 19. And add all that up. Looks to be 45. All right, so this was a very basic type of series, especially because it's finite, right? Because it only went from 0 to 4. It's finite, and they're good to take a look at introductory wise. But then we have to eventually get into a much deeper realm, right? And look at more so those that are not finite. All right, so we're gonna have to look at infinite series, and then determine if they converge or diverge. So first things first, we need to take a look at something important for us. And that something important is called the nth term divergence test. The nth term divergence test. So with using an infinite series, if the infinite series fails this test, then it's automatically divergent, right? If an infinite series fails, then it's divergent automatically. All right, and then we're done with it. So the nth term divergence test should be the first thing you do to an infinite series when you see one. All right, so here it is. The infinite series, we have sigma a sub n, is divergent if the limit of a sub n as n approaches infinity does not equal 0. All right, so if you think about this, if you're adding an infinitely long list of numbers together, there's no way you can get a finite sum unless you're eventually adding 0 or something close to it, right? Infinitely. Right, so for example, if you have the limit of a sub n, right, as n approaches infinity is equal to 1/2, then you're eventually adding 1/2 plus 1/2 plus 1/2 plus 1/2, so on and so on, forever and ever. And then that sum will get infinitely large, right? Half a unit at a time. Get infinitely large, a half a unit at a time, forever and ever. And then that would cause the series to diverge. And the last piece of information on this test, you can't use the nth term divergence test to prove that a series converges. You cannot. It only proves divergence. Only proves divergence. All right, so we have here a geometric series. So the geometric series is pretty easy to spot. All of the terms will contain some common factor, and then once it's factored out, the result is going to be a number raised to consecutive powers, right? So all geometric series have the form where we have sigma n is equal to 0 to infinity a r raised to the n, where a is that constant every term has in common. A is the constant that every term has in common, right? And R is the ratio, right? I said that A is the constant every term has in common. R is the ratio. It's the number that's raised to consecutive powers to generate the series. So again, when the series is expanded, every term will contain A, and consecutive terms are going to possess consecutive powers of R, which is called the ratio. So the geometric series begins with n equals 0. So this creates the effect of making the first term A when the series is written as a sum. So we have n is equal to 0, is equal to infinity, AR raised to the n, A plus AR plus AR squared plus AR cubed, and so on. And then a geometric series will converge if r is between 0 and 1. It will diverge if the absolute value of r is greater than or equal to 1. If the series converges, you can also find the sum of the series by plugging into the formula a over 1 minus r. All right, quick side note, a point that you should know. Just like, let's say, if you recall, when you're doing integrals, you have some constant a multiplied times some function, right? And you're trying to integrate that. What can you do? You can take that constant and pull it out in front of the integral, right? So you can pull constants out with sigma notation just like that. So if we had sigma a and f of n, we can pull that constant out in front just like we did with integration and do it just like that. You can pull constants out of sigma notation just like with integrals. All right, so our example says to determine whether or not the geometric series of 2 plus 3 plus 9 halves plus 27 fourths plus 81 eighths and so on converges. And if it does, if so, give the sum of the series. Okay, so the problem tells you that it's a geometric series, so that's good. The first term is the a term, right? Then we know that. The first term is the a term. And if you factor it out of everything, let's do that, then you'll get 2. We factor out a 2, and I'm factoring out of what they gave us, the 2 out of everything. We get 2, 1, and what's the next one? Oh, we get 3. Say 3 halves, right? That'll get us the 3 back. Plus 2 times 9 fourths will give us 9 halves. Okay, and then 27 eighths, and then 81 sixteenths. So the ratio here in this series, r equals 3 halves, right? Because the terms in the expansion are consecutive powers of that fraction, right? The terms in expansion are consecutive powers, right? 3 halves to the 0 power is that 1. 3 halves to the first power, 3 halves. 3 halves to the second power, 9 fourths. And let's keep on. 3 halves to the third power is 27 eighths, right? And etc. So then rewrite the series in geometric form. Rewrite the series in geometric form. So it's going to be sigma n is equal to 0 to infinity 2 times ratio 3 halves raised to the n power. All right, so looking at this, since that absolute value of 3 halves is greater than or equal to 1, then this series will diverge. This series will diverge, and as such, will have no finite sum. Will have no finite sum. All right.